So this thing that we've been writing down, products divided by reactants, everything raised to their stoichiometric coefficient, is called the law of mass action, or the so-called mass action expression. And so this ratio that we have of the activities is this mass action expression, and it is equal to K when the concentrations are the equilibrium concentrations. So really, again, if I have my generic version, A moles of A plus B moles of B makes C moles of C plus D moles of D. Really, this is K is the concentration of C raised to the power C. This is the equilibrium concentration. Concentration of D raised to the power D. This is the equilibrium concentration. Concentration of A, equilibrium. Concentration of B raised to the power B, equilibrium. So it's only equal to K if the concentrations I have are the equilibrium concentrations. If I have just the instantaneous concentrations, then I have my so-called reaction quotient. That is, when I'm looking at the concentrations which are just any old value, what I happen to have right now, the mass action expression gives me Q. But if the concentrations that are in my expression are the equilibrium concentrations, then I have K. And I'll just tell you right now that it gets to be a huge pain to write these little equilibriums on there all the time. And so what will happen is I will drop them off and they won't show up. Technically, if I go back here and look at this one, K is the partial pressure of NH3 at equilibrium squared times the partial pressure of H2 at equilibrium cubed times the partial pressure of N2 at equilibrium. But I'm going to be really lazy, and I'm just not going to write these little at equilibriums because it gets to be a pain. And so we're going to have to just remember that when we're talking about K, we're talking about equilibrium expressions, and when we're talking about Q, we're talking about instantaneous concentrations. So now we got to think about K and how to manipulate it, and there's actually a specific learning module on this. But a very important idea is, of course, that since K depends on the balanced equation, what are the stoichiometric coefficients, what are reactants, and what are products? If we manipulate that balanced equation, we change K. So for instance, here's my first expression, A moles of A plus B moles of B makes C moles of C and D moles of D. If that is K1, then what happens if I write the thing backwards? Now I've just switched products and if I do this as concentrations, I've got K is C moles of C, D raised to the power D, products divided by my reactants. Now what happens if I switch products and reactants? I'm going to flip these around. And so if I write the reaction backwards, now K2 for my reaction backwards, now A is on top and B is on top. And C is on the bottom and D is on the bottom because I've switched my definition of products and reactants. And so that means K1 is equal to 1 over K2, or K2 is equal to 1 over K1. The same is true if you take the whole thing and you multiply it by 2. Then you're going to have to square everything. And so there's a relationship between what happens if you multiply the whole reaction by a stoichiometric coefficient. Most important thing to remember, for the equilibrium constant to have any meaning at all, it must go with a balanced equation. Gas reactions, they're a pain, because some people like concentrations and some people like partial pressures. Technically, it should always be partial pressures. And if I could make the whole world go back and promise to never do a gas reaction as concentration again, I would. But you're going to see lots of gas reactions written as concentrations. So we need to think about how to convert between concentrations and partial pressures for equilibrium constants for gases. So for Kc, I'm going to note that I'm making this in terms of concentrations. And now it's the concentration of my products raised to the power 2 because I've got 2 moles. Concentration of H2 cubed because I've got 3 moles. Concentration of N2. But if I wrote it in terms of partial pressures, Kp, that was be the partial pressure of NH3 squared over the partial pressure of H2 cubed over the partial pressure of N2. Now these are not the same, but they can be converted into one another. And the reason is because I can write the partial pressure in terms of the concentration. And so I can actually convert back and forth between these two. So let's see how we can do that. What we need to do is remember what partial pressure is. Partial pressure of some compound I is the number of moles of I times RT divided by the volume. Now, the number of moles divided by the volume, that's just the concentration. And so the partial pressure is just the concentration of I times RT. And so I can convert back and forth between these two because there's just a factor of RT. You can try to memorize some formula for what it should be, but if you just remember what I did right now, you can always go back and forth between concentration and partial pressure. All right, 2 kinds of equilibria, homogeneous versus heterogeneous. Homogeneous means all the chemical species are in the same phase. That's like I have something in solution and it's just all ions. No solids, just aqueous stuff surrounded by solvent. Or it's a gas phase reaction. Everything's up in the gas phase. No solids, no solvated ions, no nothing. Heterogeneous means any of the chemical species is in a different phase. And so anytime you have that, what that means is that the definition of the activity will differ for different substances. So for instance, if I look at this first reaction, this is calcium carbonate solid decomposes into solid calcium oxide and CO2 gas. So I've got solids and gases, clearly a heterogeneous reaction. So what is the mass action expression? It's the activity of calcium oxide solid times the activity of CO2 gas divided by the activity of calcium carbonate solid. So those have different definitions because some are solids and some are gases. And in fact, this is just one, and this is just one, and this is just the partial pressure of CO2. And so in the end, K just comes out to be the partial pressure of CO2. That's all that's left because the solids and liquids go away. What about some of these other reactions? Well, if I look at this reaction, this is going to be solid and 2 gases. I know the solid's just going to disappear. So what do I get here? K is going to be the product, which is a gas, the partial pressure of this nickel carbonate divided by, sorry, I'm having trouble with this reaction because I find it very hard to believe that this compound is a gas, divided by the pressure of CO to the 4th power. Okay, that's definitely how it works as is. I'm a little worried that that's not actually a gas. What about this last one? This last one, well, this is just like what we've done, right? This is just a solubility expression. We've got calcium hydroxide solid goes to aqueous calcium and 2 hydroxide ions. So what's K for that? It's just the concentration of calcium times the hydroxide ion concentration squared. Where's the solid? You're just dividing by 1 because the activity of the solid is 1. What does the value of K tell you in general? We want to divide the world up into 2 situations. K is greater than 1, K is less than 1. What is K? K is pretty much the activities, it is the activities, but it's the concentrations or partial pressures of the products divided by the partial pressure of the reactant. So if there's more products than reactants, K will be greater than 1. So this is more products. More products than what? More products than reactants. And such a reaction, we would say, favors the products. Does it mean it's 100% products? No, but it's mostly products. Conversely, K less than 1, that's going to be a reaction that favors the reactants. And so we've written it down as if it's reactants goes to products, but it turns out that it only goes to a little tiny bit of products. And so such a reaction would favor the reactants. Very, very, very important idea. The equilibrium constant does not depend on the starting conditions. So here are the results of three experiments for my reaction from earlier. 1 mole nitrogen, 3 moles hydrogen makes 2 moles of ammonia. And I start out with different conditions. Here I start out with a mole of nitrogen and a mole of hydrogen. And then I let the whole thing come to equilibrium, and lo and behold, I have a little nitrogen left. I have some hydrogen left. You see, I have less because for every mole of nitrogen, I've used 3 moles of hydrogen. And then I made some ammonia. If I take these concentrations and I plug them into Kc here, I get some value for the equilibrium constant at this, under these conditions. So this is a really simple type of problem. If you are given all of the equilibrium concentrations, you can just plug them into the mass action expression and tell me what the equilibrium constant is. Now let's imagine we started the reaction somewhere else. Now I don't have any nitrogen or hydrogen. It's all ammonia to start with. So into my container, I've put 100% ammonia, 1 mole of ammonia, or 1 molar ammonia in my container. And now the reaction actually goes backwards, and it generates nitrogen and hydrogen. And again, it makes 3 times the hydrogen compared to nitrogen because there are 3 moles of hydrogen for every nitrogen that is formed. I plug all of those into the mass action expression, and I get the same number. Totally different concentrations, completely different conditions. So the equilibrium doesn't always end with exactly the same ratios of concentrations. But when I put them into the mass action expression, it works out. So here, it's mostly nitrogen in the first example, but in the second example, it's mostly hydrogen. And when you put it all in and square it and cube it, it all comes out to be exactly the same thing. And here you can start it off with a little bit of everything. 2 molar of this, 1 molar of this, 3 molar of that. Let it all go to equilibrium. What do you get? A whole bunch of stuff. And now exactly the same concentration. So every condition ends up the same. But what is the same is the value of the equilibrium constant. The individual concentrations can vary, and the ratio between any 2 of them can vary. Because we're squaring and cubing things, it doesn't work out to a simple relationship.